Seniors last week, and we do have at least one senior in this class, I think. Yep, we do have one senior in this class, so it does affect somebody in here. But this is the last week of classes for seniors. Next week, if you have to take the final as a senior next week, you do it during class. So I set up a breakout room, move seniors to a breakout room, and they take the final. But remember, you can be exempt from the final semester in this class. So hopefully that's the goal of everybody, right? No missing assignments. Hopefully you haven't had more than 4 absences or tardies, haven't had more than 4 absences in advisory, and a grade of at least 75%. So if you meet everything but the grade, man, I'd go back and redo some lower grades, get that grade of over 75%, and be exempt if at all possible. So absolutely good to see, man. We got a lot of people in here already, a lot of cameras on. You guys are awesome. This class rocks, I tell you. Even though it's my largest class, you guys are killing it. You guys do really well. So right now we have 2 people with the possibility of failing. And I don't think either one of them has turned anything in since spring break, so it's no surprise that they're on the verge of failing or already failing. So I don't think either one of them are in class right now either. So speaking to the choir here. But anyway, yes, last week of class for seniors. And for those of us who are not leaving after this week, we got next week, and then the week after that is finals. And then technically our last day of class is the day after Memorial Day. But I think we're working on some community service opportunities and other things. More information to come. But anyway, yes, so finals for seniors. If you're not exempt, Monday and Tuesday next week, you just go to your normal class periods, set up a breakout room, and seniors will do that. You're still good, Josh. We just got started. Just getting started here. So we're right at it. So we'll have a lesson this week, and then we'll have next week, and then the week after that's finals. Seniors, this is your last assignment. All right. Get this set up so we can jump into our lesson because we're doing geometric series and sequences this week. Remember last week we were on algebraic, so hopefully you still got those notes from last week because you can use them on the exam. I guess we're doing the exam next week, just over these 2 things. So get your pencil and paper ready because we're going to do equations for geometric sequences and geometric series this week, so that you'll be able to, and with all of those equations from last week and this week, well, you can nail the test next week, be in great shape. Let's see. Yeah, I meant to mention that at the beginning of class. All right, if we go to our grade screen, we scroll down here, we are Module 7. You should have turned in the arithmetic sequences and series that we did last week. And so you see this week we have geometric sequences and series, 2 different lessons, and then the test next week. And then we'll have the final. So, and the final you can be exempt from. But again, if you have all the equations from last week and the ones from this week, you shouldn't have any trouble with sequences and series. Next week will be great. But let's jump into it so we can get all these notes behind us and be ready. All right, this is another one like we started last week. I'm going to find the next 3 terms in the sequence. Let me blow this up a little bit. In the chat, put what are the next 3 looking at the sequence. Now, remember last week we had like 2, 4, 6, 8. And it's real easy. We said, oh, it's 10, 12. You know, we just added 2 every time. This is not adding, because we went from 1 to 4 and 4 to 16. This is a little different. You got to recognize the pattern. What's going on to go from 1 to 4 and go from 4 to 16. And then what would the next 3 numbers be? Anybody? One, 4, 16. Seth jumped on the pattern there. He says, if you look and see what's happening, it's multiplying by 4 every time. Right? To go from 1 to 4, you just take 1 times 4. To go from 4 to 16, you take 4 times 4. So to go to the next number, we take 16 times 4, and that'll put us to 64. Take 64 times 4, that'll put 256. Take that times 4, that's going to put it at 1,024. So that should be the next three terms multiplying. If you weren't sure, you can always work backwards. Let's open up the calculator and just show you how you do that. If you're a little lost, some of these are kind of tricky. Just take the second one and divide it by the first one. So what's 4 divided by 1? Well, that's an easy one. Take the third one and divide it by the one in front of it. Just divide by the one in front of it. So if we went to 16 and divided it by 4, we get 4. So 64 divided by 16, we get 4. So we can see every time it's multiplying by 4. All right, let's look at the next one. Oh, 2, -6, +18. What sequence is going on here? What's our next term on this one? You don't know the pattern, go backwards and divide. Divide by the number in front. Pick a number and then divide by the one in front of it. And you should see every time it's multiplying by the same number. So you just apply that going forward. 2, -6. Okay, Mary's figured out the pattern. This one is multiplying by -3. Not just 3, it's -3. You know, 2 times 3 is 6, 6 times 3 is 18. But to get that negative every other term, so 18 divided times multiplied by -3 be -54. And then when you multiply this one, it becomes a positive again, right? Because now we're multiplying a negative times a negative. So we'll go to 162. Then we've got to multiply that by 3, but it's a negative. So a positive times a negative. So it's going to cycle every other time. Positive, negative, positive, negative, positive, negative. But certainly it's a valid sequence. We're just multiplying by a negative number. So it's going to bounce back and forth. Now, graphing this would look really weird because our graph's going to have points that are going up and down, up and down, up and down. But this is just a sequence of numbers, geometric. So you may have figured out geometric sequences work exponentially because it's multiplying. Where our sequences last week, the arithmetic, they just added. So it's very constant. See how we do. Excellent. There we go. All right, our third one. Now, I don't know why they put a $sign after the number. But it's $1, $1/2 $1, $1/4 of a dollar. But they put $signs before and after. That's just kind of weird. I wonder if that was a mistake. But what is the next number here? Without a $sign. We're putting them, we're just going to type in the numbers. Yeah, 1/8. If you look at it, it's 1/1, 1/2, 1/4, 1/8, 1/16, 1/30. The bottom number is doubling. You're multiplying it times 1/2. So when you multiply by 1/2, the top is being multiplied by 1, so it doesn't change. The bottom is being multiplied by 2, so it doubles. 1, 1/2, 1/4, 1/8, 1/16, 1/32. There they are. And they put those weird $signs all around. But that's the right numbers. Last one. So save the best for last here. 6, -1.2, +0.24. This is another one of those alternating ones. Positive, negative, positive, negative, positive, negative. So obviously the factor that we're multiplying by is a negative number because it's having to bounce back and forth. But what are we multiplying by? Again, if we're not sure, just pick the number and divide it by the one in front of it. So let's go 0.24 divided by -1.2. So this is multiplying by -0.2. Let's see if we get that here. Negative 1.2 divided by 6. Yes, every time we just multiply by negative 0.2. So multiplying 0.24 times that, 0.24, our next number should be negative 0.48. Or negative in front of it, there is. And then when we multiply that times negative 0.2, go hit that. There we go. Now we're going to get a positive 0.0096. Multiply that times negative 0.2. Now we got negative 0.00192. Oh, I got to put a negative on the front though. There it is. Just had to divide backwards, and we figured out it was 0.2 negative. So notice the terms in each sequence are separated by a common multiplier. We call it a common ratio. Last week we called it a common difference because we were adding, what's the difference between the numbers when you subtract one from the other? This is a ratio. So like in the first one we had 1, 4, 16, they're all separated by a common ratio of 4. Each one is 4 times larger than the one in front of it. That's the ratio. A common ratio. First term 1 is multiplied by 4, 4 is multiplied by 4, as a result. This is a geometric sequence. So we're going to learn how can an expression or process be determined for a geometric sequence, what functions combine to create an explicit formula. We had a recursive formula and an explicit formula last week. And what possible restrictions exist in the domain and range, just like we talked about last week. All right, let me shrink this back down. So go to page 2. All right, a geometric sequence is a list of numbers, which we again call terms, which share a common ratio. So we're going to look at some more sequences here. Some of these are geometric, while others may just be a generic series or sequence, and some are arithmetic. So we're going to separate the geometric from the non-geometric. So yes or no, is this a geometric sequence? 4, 12, 20, 28. Again, I'll make this larger so you can see it better. Yes or no, is this a geometric sequence or just some other kind of sequence of numbers? Might be an arithmetic sequence. It might be something totally generic. Dan says, no, this is not. This is not geometric because what's happening each time? 4, 12. See, if we would say, well, maybe it's times 3. 4 times 3 is 12. But 12 times 3 is not 20. What's happening is it's adding 8. Yeah, 4 plus 8 is 12. Plus 8 is 20. This is an arithmetic sequence that we looked at last week, not geometric. How about here? 5, negative 15, negative 90, positive 270. Yes or no? Is this geometric? Negative 15, negative 9. Well, there's kind of a hint in the fact that we see a positive and then 2 negatives in a row and then a positive. I mean, how could you do that? To go from a positive to a negative, you'd have to multiply it by a negative number. But then when you multiply this by a negative number, it's going to be a positive number. So it couldn't be 2 negatives in a row. So this is times negative 3, and then it's times 6, and then it's times negative 3 again. So I don't know what's going on, but it's not geometric. How about this? 1, 1, 2, 6. Geometric? Yes. Geometric? No. You can do thumbs up, thumbs down if you want to. Oh, where's that? Oh, yeah, there you go. Yeah, this one's not 1, 1, 2, 6. That's some other kind of sequence. How about this one? 7, negative 70, 700, negative 7,000. I've already seen one thumbs up. Abigail says, yep. Yeah, what's going on, Jayla? It's negative 10, right? 7 times negative 10 is negative 70. Negative 70 times negative 10 makes it a positive again, and now it's 700. And then another negative 10 goes, so yeah, we have a geometric sequence right there, our first one. How about this one? We can always check with that calculator what's going on. Let's start with the last number and divide by the one in front of it. Okay, so this is 5 times larger than that. 225 times 5 is 1125. How about going backwards from 225? 225 divided by 45. Oh, yeah, that's 5 times larger than 45. And 45 is 5 times larger than 9. So it looks like every time this is being multiplied times 5. So that is geometric. Okay, excellent. 1126. There's a pattern, but times 1, times 2, times 3, but that's not the same every time. This is geometric. We had that. This one had times negative 3, times 6, times negative 3 again. Nope. This is a ratio of negative 10 each time. We had that. And this was an arithmetic sequence. So, all right. And just like we saw with arithmetic, we could present this as a list like we just did, or we could convert it to a table or a graph. Remember, with the table, like here's our sequence, 1, 3, 9, 27. Multiplying by 3 every time. Common ratio of 3. First term is 1, second term is 3, third term is 9, fourth term is 27, and that's how we graph it. The first term, the second term, the third term, and the fourth term. And we do not connect it with a line because there's not a 1.5 term or a 3.1 term or a 3.8 term. There's only a third term and a fourth term. There's nothing in between there. So you notice there's not a continuous curve to the points I was just talking about. Okay, so there's 2 methods for determining the terms of a sequence. Recursive. Like recursive would where we know what the term in front of it is. Right, so let's get our notes started on recursive and exclusive equations for geometric. Recursive. And these are geometric. All right, recursive. So recursive, in order to find some term, a sub n, like we want to find the 5th term, all we have to do is find the common ratio and multiply it by the term in front. So if we have this 1, 3, 9, 27, right? Our common ratio, we use R for this. We use D for common difference, right? Common ratio. R equals 3, a positive 3. 1 times 3, 3 times 3, 9 times 3. So if we want to find the 5th term using our formula, we take our common ratio of 3 and we multiply it by n minus 1. N is 5, so this would be 5 minus 1 by the 4th term, which is 27. That's a sub 4. So that makes our next term 81. A sub 5 is 81. Just using our recursive formula. Whatever the term in front of it is, multiplied by the common ratio. Simple enough. We can understand that. And that's what they're showing us right down here. This is using a sequence that says multiply by 4. So this has a common ratio of 4. So its formula is a sub n equals 4 times a sub n minus 1. So if you know the first term is 3, to find the second term, you just take the common ratio of 4 and multiply it by that 3. It's 12. So 12 is a sub 2. So to find a sub 3, the third term, you take 4 times a sub 3 minus 1, which means the second term, a sub 2, which is 12, and we'll get 48. And then the next one's 192, and you just keep going. Now let's talk about the explicit formula. Just like in arithmetic, we could jump straight to the 12th term without having to know the 11th term. If we can come up with an explicit formula to just immediately calculate, like you can list each item until you reach the 27th, and who's got time for that if we want the 27th term of this sequence? So let's figure out how to get the explicit formula. All right, at this point, you should understand how to identify geometric sequence because we looked at how to find the next term. But what if we were asked to find the 11th term of a sequence that goes 2, -6? All right, here we go. Let's do this, and then we'll come up with our other formula here in just a minute. So we want to find the 11th term, and the sequence is 2, -6, 18, -54. So I'm writing that down here. We want the 11th term of this sequence. So the first thing we need to know is what is the common ratio to get from 2 to -6, -6 to 18, 18 to -4. You can divide backwards if you can't see the pattern. Our common ratio is -3. 2 times -3 is -6. -6 times -3 is a positive 18. 18 times -3, -54. So we know our common ratio. So let's step through the little exercise here. The first term is a 2, right? And so to find the second term, what do? We multiply it by the common ratio. So 2 times the common ratio would be -6. Right? Now we see that right there, 2 times common ratio. To find the next term, the third term, we're going to multiply times the common ratio twice. We multiplied it by once to get the second term and twice. So exponentially, that would be -3 to the second power. So let me kind of make this chart just to kind of have this. First term is 2. Ooh, man, my handwriting's not going to be good today, guys. Sorry about that. Okay. So to find the second term, we know this was 2. We take 2 times the common ratio. All right, and that'll give us -6. Then to find the next term, if we started with the first term, once we multiplied it by a -3, that gave us the second term. So if we multiply it by another -3, that'll give us the next term, the third term, right? Because first term, this gets us the second term, that gets us the third term. Well, this is the same as 2 times -3 squared. -3 times -3 is 9 times 2. That gives us 18. We want the fourth term. Not good handwriting today. We take the first term, and when we multiply it by 1 -3, that gave us the second term. That gave us the third term. To get the fourth term, we again multiply by another -3. So basically, we multiplied 2 times -3 3 times. So that's cubed. So -3 times -3 times -3. Well, -3 times -3 is +9 times another -3 is a -27 times 2. Excuse me. So from this, we can come up with an explicit formula. If we want to find any term, a sub n, How do we do it? If I want to find the fourth term, a sub 4, I start with the first term because that 2 was our first term up there. So we start with a sub 1 and we multiply it by, this is the common ratio, but it's raised to a power. And what power is it raised to? Well, this was the fourth term, and we raised it to the third power. This was the third term, and we raised it to the second power. This was the second term. We just raised it to the first power. Each time, the power that we're raising it to is 1 less than our term. Fourth term, 3. Third term, 2. Second term, 1. So this is raised to the power of n minus 1. That's our explicit formula. If I want the sixth term, I'll take the first term times the common ratio to the n minus 1 or fifth. So we want the 11th term. So if we want a sub 11, using our formula that we have, we take the first term, which was a 2. Our common ratio is a -3. And this is n minus 1, 11 minus 1, because a sub n, we want the 11th term. So that means we want 2 times -3 to the 10th power. And let's see what that equals. We'll our calculator back up. 2 times, and I'm going to parentheses, -3 raised to the power of 10. So 2 times -3 to the 10th power, it's an awful big number. But remember, we're growing exponentially. Not surprising that's an awful big number. Because when you're multiplying by something by -3 each time, 3 times bigger, 3 times bigger, 3 times bigger, positive, negative, alternating. 118,098. Let's see what they got. See if we got the wrong ballpark. So there's the fourth term. So they come up. All right, so where's the 2 originate? That's the first term. The -3 is the common ratio. The exponent is determined. It's 1 less than the term number, sequence minus 1. What's the fifth term? 162. Yeah, we didn't get to the sixth term. But it wanted to know what was the 11th term. So let's see, does this video give us the 11th term? Or just give us the formula?
The fifth term of the geometric sequence is 162. 162 can be written as 2 times 81. 2 represents the first term in the sequence, which is indicated as a sub 1. 81 is the result of 162 divided by 2. 81 can be written as -3 to the 4th power, where -3 represents the common ratio between each term of the sequence. 4 is the result of the exponential equation 81 equals -3 to the power of x. Use the variable r to indicate the common ratio. 4 is the same as 5 minus 1. 5 represents the fifth term in the sequence, and 1 is the difference between 5 and 4. The variable n is used to represent the position of the term in the sequence.
All right, so there it is. That's the formula we just wrote down in our notes. A sub n equals the first term times the common ratio raised to the power of n minus 1, whichever term we're looking for. N minus 1. All right, let me switch this back before I forget about it. So there is the formula right there. What do the variables mean? You know, A sub n is the number we're looking for. A sub 1 is the first term. R is the common ratio. And then n is, the position of the term in the sequence. So here's that answer, A sub 11. 118,098. That is the number that we came up with. We just had to come up with this formula and then just plug in the numbers. So we got that. Important note. You may be thinking that a geometric sequence formula looks remarkably like an exponential function, like f of x is 3 to the x. You're correct. Geometric sequences are used for events that are more static in nature, where exponential functions support continuous events. Like interest rates that are only applied once a year to a savings account could be expressed as a geometric sequence. But savings accounts which earn interest continuously would be expressed as an exponential function. So yes, they're very similar, very related. So converting recursive and explicit. The recursive is a sub n is common ratio times the term in front of it, a sub n minus 1. The explicit a sub n first term time common ratio n minus 1. So n minus 1 and n and r are in both equations. You just got to pay attention to where they're used and know how to come up with what you need there. Combination of functions. They like talking about these separately. A sub 1 is the first term. That's a constant. The first term of the sequence is always going to be the first term of the sequence. That doesn't change. That's a constant. The common ratio raised to the power of n minus 1, that's going to change depending on n. Are you looking at the 5th term? You're looking for the 38th term? You're looking for the 11th term? That's going to change the value of that. First term is always going to be whatever the first term is. So when you combine these, you combine them by multiplying. Multiply that constant times that variable r to the n minus 1. So they will probably have a problem that you do again where it gives you and says, combine these. Well, combine them by multiplying, because that's how the formula works. We had some last week, even though it was adding, some people subtracted it. It's like, combine these. Well, yeah, with arithmetic, we add them together. So these we multiply. And the domain and range, this is very, very much like last week's conversation. The domain is going to be all integers greater than or equal to 1. Again, because what is the domain? That's the term number. First term, second term, third term, fourth term. We do not have a 0th term. We do not have a negative third term. We do not have a 4.68 term. We only have the counting numbers. 1, 2, 3, 4, 5. First term, second term. If I told the class, I said, all right, let's get in line. I can say, who's the second person in line? You could tell me who the second person in line was. If I ask who's the negative 5th person in time, everyone would be confused. What do you mean negative 5th, Mr. Brock? You mean starting from the back? No, that's not negative. Yeah, there is none. Who's the 7.3 person in line? There's not one. Domain is and the range can be anything again, depending on your sequence. We saw range that got up to 118,000 by 11 terms. When we were looking at the sample at the beginning, we had some of them went positive, negative, positive, negative. So it could be any number. Any number. Doesn't have the same restrictions. All right, let's do a couple of examples, and then we'll have our lesson summary. Then we can go to the geometric series, because we've got to hit that today. So let's do just this first example. And you can do this on your own, because I want to get to the series. All right, we want to know the 14th term of a sequence where a sub 1 is 6, a sub 8 is negative 468, 750. Whew, that's a fun one. Okay, we want to know the 14th term. The first term is 6. The 8th term is negative 468, 750. So we have our two formulas. Let me highlight these so we have them on our notes and can quickly find them. So looking at that, this doesn't help me much. Okay, you got to know the term in front of it. We know an 8th term and the term that's a first term. This, however, looks very useful. Because a sub n, if this was 8, a sub 8 I could use a sub 8 equals a sub 1 times r to the 8 minus 1. Because I know I have the 8th term. So I can do this and just substitute what I know. What is a sub 8? Well, a sub 8 is negative 468, 750. What is a sub 1? A sub 1 is 6 r to the 7th. I could put that inside the parentheses, r to the 7th, but no, that's what they are. So to find this, let's just do a little math. We're trying to get r by itself, so let's divide by 6. And that'll tell us what r to the 7th is. So 468, 750 as a negative divided by 6. Negative 78, 125 equals r to the 7th power. R to the 7th power. So to find r, I got to take the 7th root. What number multiplied by itself 7 times gives us this? Well, our calculator is happy to help us do that. Right here on the front page, this has got a square root. But if I shift, I've got a 3rd root and a what root do you want button. It shows the y root of x. And in Buzz, the calculator can do the same thing. So I'm going to put this 78, 125 negative, hit this y to the x, and now it's going to say, okay, what root do you want? I want the 7th root. Oh, it's negative 5. Look at there. R equals negative 5. Negative 5 to the 7th power, to the 7th power is the 78, 125 negative. So this is our common ratio. So to find the 14th, I want to know the 14th, a sub 14 would be the first one, 6 times the common ratio. We know the common ratio now, to the 13th. N is 14, so this is n minus 1. So let's put this in our calculator. 6 times parentheses negative 5 raised to the power of 13. So the 14th term is going to be negative 7 billion 324 million 218,750. Remember, this is exponential. Exponential numbers grow really, really quickly. Let's see if we're right. So first you got to find what r is, which we did, working backwards. Found that was negative 5. So then find the 14th term, and it is negative 7 billion 324 million 218,750. That's the 14th term. When you're multiplying each term by negative 5, it gets big really quickly. All right. So that's example 1. There's another example there too. I'll let you work through that. Here's the lesson summary. Here is the recursive and the explicit. So this one right here that they give you is the same as the explicit. Because that's what you're going to find more useful more often. Because this, you have to know the number right in front of it. And we don't often have that. Okay. It's right in my way. Then they give you some practice problems here. Find the 10th term of the sequence 2, 8, 32. So if we got your common ratio, this time obviously it's 4. 2 times 8. 2 times 4 is 8. 8 times 4 is 32. Use your formula to find the 10th term. I guarantee you it's going to be a lot bigger than 38 because you're multiplying by 4 every time. 5 problems there. Let's look at our assignment. Then we're going to look at our series before we run out of time. Find the 16th term where here's the first term, here's the 8th term. Find the 17th term where here's the first term, here's the 5th term. Round the common ratio and the 17th term to the nearest hundredth, 2 decimals. So if you don't round the common ratio first, and if you're working this, and let's just say, for example, you got 30,710.6. That's probably telling you this is the right answer. It's just a rounding thing. So if you get something close to one of these numbers, just assume the rounding is why you're off. Now, if you get 250,000, that your rounding ain't going to be off 34,000. But if it's just off by a little bit over here on tens or ones or just decimals, rounding can cause some issues. Let's see, a bacteria culture begins with 15 bacteria, which doubles every hour. How many is in the 12th hour? Well, you get your common ratio. If it doubles, it's 2. So you start with 15 as your first term, and then you can go to the 12th hour. So see which one of those you get. Here's one of those. Given the function f of n equals 500 and g of n is 9/10 to the n minus 1, combine them. Do you subtract them? Do you add them? Do you multiply them? Or do you multiply the 500 times the 9/10 and then take the n minus 1? This one you shouldn't even have to solve for the 11th term because only one of these equations is correct. And here's this geometric sequence in a table. First term is 3, second term is -6, third term is 12. Create the formula and list any restrictions to the domain. You can eliminate 2 of them real quickly. All right, so that's our first assignment for the week. Let's look at the geometric series so we can get those formulas in our notes. Okay, another video. Let's switch to that then. I think that's one of those little goofy cartoons that they like to do.
Rachel's mother just returned from a vacation to Moscow. She brought back a set of matryoshka, or nesting dolls, for Rachel. Nesting dolls are a series of dolls that open up so that each doll contains a smaller doll until you get to the smallest, innermost doll. The packaging that came with the dolls notes that there are 8 dolls and each doll is 10% smaller than the previous one. Rachel has a 2-foot-long shelf in her room, but it's covered in small dolls already. She doesn't want to clear it unless she knows the nesting dolls will fit. First, she measures the largest doll. At its widest, it is 5 inches long. Rachel does not want to find 90% of 5 inches, then 90% of that number, and so on 8 times over. So instead, she uses a special way of adding numbers that change by a constant percent. The first doll is 5 inches wide. The next doll is 5 inches times 0.9 because it is 10% smaller. The next doll is 5 inches times 0.9 squared because it is 10% smaller than the previous doll. Rachel can find all of the doll's widths this way. She knows that when a number is multiplied repeatedly by the same constant, the sequence of products is called a geometric sequence. In this lesson, you will see how to add terms quickly in a geometric sequence. This sum is called a geometric series. You can use it to see if the nesting dolls will fit on Rachel's shelf. You find the sum of a geometric series using the formula S sub n equals a sub 1 minus a sub n times r all over 1 minus r. S sub n is the sum up to the nth term. In this case, you want 8 terms added. A sub 1 is the first term, and a sub n is the last term. So here, a sub 1 is 5, and a sub n is 5 times 0.9 to the 7th power. R stands for the common ratio, and is the factor that each term is multiplied by. In this case, r is 0.9. So substitute and solve. The dolls will span about 28.5 inches, or just over 2 feet and 4 inches. Rachel's 2-foot shelf is not enough.
All right. Love Rachel. She's a real math nerd because she wanted to come up with a formula to figure this out. Where even me, as big a math nerd as I would have just pulled them out all of the box, set them on the table, and measured how long they are. And said, nope, that's too long. And then see if I could kind of scoot them like kind of diagonal and make them all fit. Then I can clear off the shelf. She's even nerdier than I am because she wants to do a formula. Love it. So how do geometric sequences and series differ? And what information must be included to find the sum? So just like arithmetic series is adding up a sequence, same thing here. We're adding up a geometric sequence. All right, so here's another one of these where we got to know which one is a sequence, which one is a series. So let's blow it up one more time. Let's see, a geometric series is a sum, adding them all together. So the terms in the geometric series are separated by a common ratio rather than a common difference. Let's look at these numbers. 1, 5, 25. Well, that's obviously a sequence. That's what we did last lesson that we just looked at. Sequence of numbers. 4, negative 32, 256. Well, this is multiplying by negative 8 every time. It's just a sequence of numbers. But look here. 3 plus 6 plus 12. The common ratio is 2. It's multiplying by 2 each time. 3 times 2, 6 times 2. But they're adding it together, so that's a series of numbers. This is one of those alternating. We have a positive, negative, positive, negative, positive, negative. But we're actually doing the math of adding those together. That's a series. So just know the difference between a sequence and a series. That sequence is just separated by commas. We're just listing all the numbers out. But a series is where we're adding them all together to come to one total of however many terms that we're wanting to add. Oh, this is good. I'll make this larger here. So again, the important thing is when working with these arithmetic or geometric is knowing what these little terms mean, because we're using them in all of our formulas. A sub n, is that the first number in the sequence? Is that the common ratio between the terms? Is that the sum total of the numbers? Is that the number of terms in the sequence? Or is that the value of the nth term in the sequence? Well, A sub n, we're talking about a specific term. If we want to know the 9th term, then we're talking about A sub 9. So that would be the value of the specific nth term of the sequence. A sub 1. A sub 1 always means the same thing. It always means the very first number of your sequence. And that doesn't matter if it's arithmetic or it doesn't matter if it's geometric. A sub 1 is the first term. N would be the number of terms. All right? If we're doing a series, we're adding up to A sub 9. And we want the first 9 terms. There's 9 terms. R is that common ratio. Remember, it was D for arithmetic because there's a difference. This is a ratio. And S sub n. S means sum, just like it did with arithmetic. That means we're taking the sum total of the n numbers of the sequence. Okay, so now let's find the formula for finding the sum, which I think they just gave us in the video because I wrote it down. What is the first term of the series? 3 plus 6 plus 12 plus 24 plus 48 plus 96. Well, 3. First term is the first term is the first term. What is the common ratio? Well, it goes from 3 to 6 to 12 to 24. It looks like it's times 2. Times 2. And what is the sum of the series? Well, 3 plus 6 is 9, plus 12 is 21. 21 plus 24 is 45. 45 plus 48 is 93. 93 plus 96 is 189. So it's 189 when we add them together. So this is pretty simple. There's few terms, and each of the terms are pretty small. We're not dealing with any 7 billion. We just dealt with 96 was our largest. So, but we'll be working with series that have many more terms, so we need to have the formula. So let's look at the little video again. All right, finding the geometric series formula. No audio. So the first term is 3. So I said, okay, what if we just factor a 3 out of every term? Because it should be, since we're multiplying every time to get the next one. So 3 times 2, 3 times 4, 3 times 8, 3 times 16, and 96 is 3 times 32. So the common ratio is 2, because looking at what's left after we factored that out, 2, 4, 8, 16, 32. I paused it here. 2, 4, 8, 16, 32. We can write those as powers of 2. This is 2. This is 2 squared. This is 2 to the third. 16 is 2 to the fourth. 2 times 2 times 2 times 2. 32 is 2 to the fifth. So they rewrote all those as factors of 2. Now, to find the formula, we'll just rewrite each one using the variable rather than the number you see there. Let me back up just a second. Like 3, all of the 3s, we know 3 was the first term. So we can replace all of the 3s with a sub 1. And we know 2 is the common ratio. So we'll replace all of those with r's, just to give us variables instead. 3's replaced and r's. So now each term is listed a sub 1 times the ratio, a sub 1 times the ratio squared, a sub 1 times the ratio 3 times, a sub 1 the ratio to the 4th power, a sub 1 the ratio to the 5th power. Let's multiply both sides of the equation by the common ratio. This is interesting. This will increase each exponent on the right side of the equation by 1. So we're multiplying both sides by r. That's legal. We're multiplying by the same thing. But when we do that, now notice what's happened. A sub 1 is now a sub 1 to the r power, to the first power. This one that was to the first power is to the second power, third power, fourth power, fifth power, sixth power. So by multiplying everything by an r on both sides, we got s sub 6 times r, and all these go from the first power to the sixth power. Now subtract, we're going to subtract these two equations from each other.
Oh my God.
And yes, this is subtracting. That would be like distributing a -1 in there. So it'd be
That's Lillian. Have you met Lillian?
first, yeah, distributing that negative to all the terms. And then you see these that all cancel out. Each term on the top, except for a sub 1, which didn't have an r, but you have a sub 1 r, and you're subtracting an a sub 1 r, and you have a sub 1 r2, subtracting a, and so all of these cancel out except for the very first term on the top line and the very last term, because once we multiplied by r, we created an r to the 6th power, and there wasn't an r to the 6th power up here. So when we subtract now, we're left with just s sub 6 minus s sub 6r equals a sub 1 minus a sub 1r to the 6th, because that's all didn't cancel out. So let's factor out s sub 6 to the left side, because both terms have that, which just leaves 1 minus r. And then we can divide both sides by 1 minus r to get back to s of 6 equals. And that gives us, well, this equation may work for the geometric series s of 6, 3 plus 6, 12, 98, because there's 6 terms. We need to change this s of 6, the 6th variable, to an n. So it works for every equation. Oh, don't start over. Jump to the end. Let's go see what they ended up with. So S of n equals a sub 1 minus a sub 1 r to the n 1 minus r.
Sometimes she struggles on focus. Jalen Price. Jalen Price.
Okay, that's a little different than the formula we had on the video. So we'll see if there's some differences that we can compare. So let me write down what they're giving us here. S sub n equals
Stop texting them while you're conversing.
a sub 1 minus a sub 1
You know, if you
r to the n
that makes it much more pleasant.
all divided by
Like, yeah,
1 minus r.
okay, therefore,
Okay. So that's how to find the sum of any geometric series. Well, let's see. Here's our first example. Find the sum of the geometric series 5, negative 15, 45, if there are 11 terms. And it says we need to use the a sub 1, a sub 1 r that they just gave us in the video. Okay, let's play with that then. They just gave us this equation right here.
I know, yeah.
Or series. 5, negative 15, 45, 11 terms. What is the common ratio? R equals,
We love you.
to go from 5 to negative 15, we're multiplying by 3, but it's a negative. Multiply by negative 3 each time. So that is our common ratio. So let's see if we can substitute what we know and find what the sum of the first 11 terms is. Sum of 11 terms. So it says a sub 1, that's 5,
Here, Freddie, which one are you gonna?
minus 5 times the common ratio raised to n. 5 times the common ratio raised to the 11th power. All over 1 minus negative 3 to the 11th power. Well, let's just see if we just plug that in our calculator and see if we get an answer. So let's do 5 minus 5 times parentheses here, negative 3 raised to the 11th power. So it looks like the top of our fraction equals 885,740. Put a little comma there just to help keep track of that. That's what 5 minus 5 times negative 3 to the 11th power equals. The bottom is 1 minus negative 3 to the 11th power.
Are you coming up here Wednesday or Thursday?
So 1 minus that,
Can you have your Wednesday or Thursday? What computer are you on right now?
since this negative 3 to the 11th power is a negative number, when we subtract it, we end up with a positive. So let's see what these two numbers are as a fraction. Oh, back up one. 885,740 divided by 177,148. Says if we add up the first 11 terms, we'll end up with 5, which is the first term. I think that's we did something wrong, because that's the first term. We're not going to end up back at a 5. But if we add these together, 5 plus negative 15 is negative 10, plus a positive 45 is a positive 35. Yeah, I think I've messed something up here. Let's see how they did it. Oh yeah, we're way off. What did we do differently? 5 minus
Mute yourself, bot. Mute yourself, Bryce.
5 by power. So they end up with the 885, 740 on top. So we did the top right. It's the bottom. Oh, it's just 1 minus r on the bottom. That's what I did wrong. I didn't do 1 minus r. I did 1 minus r to the n power. Where's my eraser? Yep. I didn't read the formula correctly. I had it written down correctly. 1 minus r. 1 minus negative 3. 1 minus negative 3 is just 4. That's where we got it off there. 885, 740 divided by 4. Going to add up to 221,435. That looks much more reasonable. Adding all these terms up to their first 11 terms. And that is what they got, 221,435. Okay, so obviously we need more practice with this formula because we messed that up. Let's try this thing. Sum of an 8 term with the first term 7, last term is 114,688. So let's try this on our own before we watch the video of them doing this. 114,688. I had to turn my paper over. So we need to go back and look at this. Now we had a formula here from the video that uses the first term and the last term.
Email him right now.
Let's see.
Girl, you don't send my paycheck. I'm not doing anything for you.
It did not have the parentheses. I added the parentheses. That's probably not a good thing.
I'm staring at the TV.
It just had a sub 1 minus a sub 1 times r, or a sub n times r. So I probably shouldn't add the parentheses because multiplication would come before subtraction. And if I put the parentheses, I forced the subtraction to come first. So let's try this formula and see if that works. In fact, I think I might just try it right down here.
Excuse me.
Let's see, we had first term, a sub 1 was 7, 114,688.
This price, Miss Scott just said you keep the loaner.
See if I have room down here just because same page is where my formula is. And we want the sum of the first 8 terms. Okay, so if we want the sum using this formula, like I say, I got this from the little goofy video with the dolls, and they haven't really talked about the lesson since then, but it looks like it should work for this. 7 minus a sub 8, 114,688 times the common ratio. Now here's the problem. We don't have the common ratio yet. We got to get the common ratio before we can use that. So if we go up here to our geometric sequence, we can find what the common ratio is using our explicit formula. A sub 8, way over here, a sub 8 is the first term, which is 7, common ratio of n minus 1. Well, if it's 8, then n minus 1 is 7. A sub 8 is actually 114,688. So if we divide both sides by 7,
Some classes you didn't tell you.
8 divided by 7. So this would be 16,384 is
My class, because I yell at you.
16,384 is r to the 7th power. So if we find the 7th root,
If a 0 in PE minus the only class you were texting.
7th root, r equals 4. So 4 to the 7th power is 16,384. Okay. Now we've got our common ratio of 4, and the bottom of it is just 1 minus r. 1 minus 4. So if we know the bottom of our fraction is going to be negative 3, let's see what the top equals.
I would like to see you next Tuesday in lab.
7 minus, I'm going to do some parentheses, 114,688 times 4. Close my parentheses. So this is negative 458,745, and I divide all that by negative 3, and this should give us our sum. Adds up to 152,915 if this formula was the right one to use, which I think it was. Oh yeah, we're going to find this one out by video.
No matter which formula you use, you will need to know what the common ratio is in this series. To find this unknown value, you will use the geometric sequence formula a sub n equals a sub 1 times r to the power of n minus 1.
That is the explicit one we use.
Define each variable. There are 8 terms in the sequence, so n equals 8. The first term is 7, making a sub 1 equal to 7. Finally, the last term is 114,688. Use this number for a sub n. Simplify. Now that you know the value of the common ratio, you may use either formula to find the sum of the series. However, to ensure that you have practice working with both formulas, let's use the formula S sub n equals a sub 1 minus a sub n times r all over 1 minus r.
And that is the one we use. That's the one on the left side of my notes. We'll look at it in a minute here.
The sum of an 8-term geometric sequence, if the first term is 7 and the last term is 114,688, is 152,915.
All right, and that's what we got. So we must have done that correctly. Let me put my notes back up so I can make sure you have both of these formulas written down. Okay, so we had the geometric sequence formulas, recursive and explicit. Now we have the two formulas for a geometric series. So a sub 1 minus a sub n times r over 1 minus r. Or this one's if you have the last number, right? If you want to know the sum of the first 8, you have to have the first and the 8th, which we did here. We had first and the 8th, so we could use that formula. This one does not use the 8th. If we don't know what the 8th is, maybe it says find the sum of the first 10. Well, we know the 8th, we don't know the 10th. This one just uses the first term and the common ratio. So that's the difference. Which one do I use? Well, it depends. Do you have the first and last term, or do you just have the first term? Either way, you're going to have the common ratio. but these are the two you should have for the series. These up here were sequence. See if I hold it just right, you might see them all. But this is what you want from this lesson, is these two equations right here. Now we just need to do a little practice with them to make sure we know what we're doing. We've got about 10 minutes of class left, so we'll do another practice problem. We'll make sure you got those. And they should be here in our lesson as well. Yeah, here's the lesson summary. It'll have these equations right here. A sub 1 minus A sub 1 times R to the n. That's that second one. It's on the right side of our notes, 1 minus R. Or the first one, A sub 1 minus A sub n times R over 1 minus R. Okay, let's look at another example 3. I'll let you walk through that. That's a little different type problem. Let's go to example 4 or 5. Both of them have the answers here for us as well. Okay, so this is using a table. Sebastian purchased a mega bouncy ball. Man, who doesn't love a mega bouncy ball? It says it comes back up to 83% of its original height when you drop it. So if you drop it from 100 inches, it'll bounce back up to 83 inches tall in one bounce. So he set up a yardstick and he drops it from 3 feet. And he's pretty quick because he can actually measure 2.49 feet on the bounce. I don't have a yardstick that's that accurate, but he's pretty good. Each time the ball was on its way down is considered a fall. So you know, first fall when he first dropped it at a height of 3 feet, then it came up to 2.49 feet, and then it fell again, and then it bounced back up to 2.07 feet. So basically, we have first term, second term, third term, and fourth term, and he lets it fall 12 more times. It becomes hard to measure accurately, so he wants to calculate the total distance, because here it dropped 3, and now it dropped 5.49, and now it's dropped 7.56, and you just add all these together. But he wants to calculate the total distance after he let it fall 12 more times. So let's see what we can come up with. Our first term was he first dropped it from 3 feet. Our common ratio is 0.83, right? Because that's how much it bounced up each time. 0.83. And it documents 4, but it let it fall more times. So altogether, there's 16 times that the ball fell. And before they documented, they said 12 more. So they want to know the total distance. So S of 16, we don't have the 16th bounce because it's too hard to measure, they said. So we need to use this formula. A1 minus A1Rn over 1 minus R. So A1 minus A1R to the n over n, not 7, 1 minus R. So the sum of the first 16 would be 3 minus 3 times 0.83 to the 16th power over 1 minus 0.83. So the bottom's just going to be 0.17, right? 1 minus 0.83. So we got to do some math here. So it's going to be, here, I'm just going to write this 3 minus, and let's figure out what 3 times 0.83 to the 16th is. 3 times 0.83 to the power of 16. Oh, 16. So 3 times all of that is going to be 1521846. I'll go like 7 decimal points because it's a 0 after the 6. So okay, so now we've got 3 minus the 1.52. So 3 minus 0.1 backspace 1521846 equals that. And we want to divide that by 0.17. So it dropped a total of 16.75 feet. That sounds reasonable. The first drop was 3, and the next one was 2.5, and then it was 2.1, 16.75 feet. Okay, so he's using the R equals 0.83, and A sub 1 is 3, and it's using the same equation we used. Punch all the numbers in there. They just did it down to 3 decimals. 152, well, 16.75 feet. That's it. With the 16 false. So, all right, and there's another example there you can do, and it shows you the answer again. Oh, and then here's all the dolls from the beginning of the lesson, so you can watch the other video, but we're not going to take time to do that. We need to look. Oh, there's 2 more pages of practice problems. So we're running out of time here. Oh, this is matching the terms. So here are the 4 formulas. And arithmetic sequence, arithmetic series, geometric sequence, and geometric series. So this goes from last week and this week. Which of these would match to that? That's really good to make sure you know. 2 of these are A sub n, 2 of these are S sub n. So you know the A sub n has to go with the sequences, and the S sub n has to go with the series. So if you look at it, like this one has a D, and this one has an R. The R would be the geometric sequence, where the arithmetic sequence would use the D. And then with series, we're adding the totals together. This is the A1 minus A1R to the N, 1 minus R. If it's got the R, that's a ratio for geometric. Remember, arithmetic, we had the number of terms divided by 2 times the first and last term. So that's a good one to go to. Here's like multiple problems. And which formula would you use? To find the 6th term of 2, 12, 22, which one of these would you use? Good problems there too. Make sure you know which formula to use when. And then here's some practice. Sum of the geometric sequence, if there's 10 terms, gives you the answers. 2, 3, 4, 5 problems. All right, let's look at our assignment that goes with this. Find the sum of this sequence when there's 7 terms. Which one of these is correct? Evaluate S of 5. That means adding the first 5 terms for 400, 700, 100. There's your multiple choice. 5 terms. Evaluate the 5 terms for this one. 300, 150, 75. Just about a yo-yo company says that the string rolls up by 60% of the original length. So she threw it 3 times and documented that, and she wants to know, after 10 throws, what would it add up to? 3 plus 1.8 plus 1.08 plus 7 more throws. These first 2 you can probably throw out immediately. It's not going to be 0.03 of a foot when the first time was 3 feet. It's not going to be 2.5 feet. And here's one with the table. 0th term. First term, second term, third term goes 2, 4, 8. After 10 hours, how much bacteria is there? All right, you can do that, guys. You can nail it. Whew, man, we used about all of our time up on this too. All right. Yeah, I can hit the chat while I'm there too as well. This is a B-Day Friday, so we only have class on Wednesday. If you need help, seniors, this is your last week. Right? Many seniors in here. Senior, I guess, senior. We have just one. Oh, my time just ran out. I'll get it reset. Yeah, we just have this one class on Wednesday, seniors, and then finals this next week during this class if you need to use that. Otherwise, I've turned on the GoGuardian chat. Otherwise, I'll see you guys next week. Next week, we just had the exam over last week and this week, and then we'll be moving into finals week. So school's about over. If you have missing assignments, and there are a few of you with missing assignments, get them turned in, because that's one of the things that help you qualify for an exemption. If you haven't had too many absences, you can't have any missing assignments. So get them turned in, and we'll catch you guys next time. So, all right, have a great week.